Hello everyone. Welcome in Saint-Germain-en-Laye at iXblue's headquarters for this new webinar about photonics. My name is Jean Lotiego. I'm the head of business development and sales for iXblue quantum sensors.
And I am Etienne Decerle, sales director for Micro-Optical Benches and quantum lasers.
Thank you, Etienne. Thank you for being here with us today. We'll discuss about photonics, expertise, know-how, and how it can help you in your experiment, in your developments. And before we jump in, maybe a few words about iXblue. iXblue is a French industry group specialized in inertial navigation, maritime autonomy and subsea positioning, and photonics and space. And today is a webinar dedicated to photonics because all around the world, scientists and engineers are facing more and more complex photonics setup, more and more complex experiment and products. And it's now the tipping point to translate complex setups and experiment into rationalized, engineered, and compact subsystem that helps to go faster as turnkey. Let us know, Etienne, to start with, what do you mean by transforming a lab-size experiment into a compact system?
Thanks a lot, Jean. So yeah, the idea of today is to turn your photonic lab experiment into a compact and robust system. So as shown on the picture on the left, so you can see a complete quantum laboratory experiment, okay? So you can see the size of it and how well that's a complete lab taken just for one quantum experiment. You can see on the left the photonic part of the experiment, on the right the electronic parts, and in the middle the vacuum chamber of the quantum experimentation. Our idea in iXblue is to integrate everything into a compact and robust instrument, such as this one right here. You can see here the absolute quantum gravimeter, which was installed on top of the Manhattan for more than a year. Okay. Today, we will focus on the photonic part, especially on the photonic part, but the complete iXblue's know-how is to integrate everything within instruments.
I see. And this is the path we will follow today. We'll really make sure to guide you through the expertise and the know-how to really understand what's integrated in those micro-optical benches. We'll make sure to highlight the key features. And in the end, we have selected one application to highlight and to illustrate the fact that iMOBs can be integrated in a more complex environment for more complex setup. And in the end, you notice that we will welcome questions. So on your webpage, feel free to send us your question in the chat box so that we can answer them live. And anyway, our entire team will be available later on after a good night of sleep to take your question by email if you missed it. But now that we dive into the topic, why do we use iMOB?
So why do we use iMOB? The idea is clearly to integrate all the photonic part of your experiment inside a component. On the left of this screen, of this slide, you can see the photonic experiment which was made in Xatom, our colleagues in Bordeaux. Thanks a lot, guys, for the picture, by the way. This experiment was requested to be integrated inside a component such as this one on the right, okay? So you can see how we could compacify everything. You can see the side of an FC APC connector right here and an FC APC connector right over there. You can see how we could compacify it, and you can easily understand how it's easier for them to handle it, okay? Now it doesn't need to be realigned, it doesn't move, it is much more reliable, much more repeatable for them. It's a great help for them in order to be able to achieve more precise, more accurate measurements. And in the end, it's a lot of time gained for their experimentations. So that's the idea of an iMOB. That's how we do that. That's what we aim to do for you if requested.
Okay. So more compact, robust, but say that I want to integrate complex optical functions. How do you manufacture the iMOBs?
The manufacture of an iMOB is depending on our know-how regarding the glue-in method and the active alignment method that we are using. Okay. On the bottom of the slide, you can see one of the micro-optic bench that we are assembling every day, okay? Our knowledge is regarding the gluing, and as we are gluing actively aligned, so actively means that we input some optical power inside, we can achieve high specs in terms of insertion loss, of PER, of stability, and so on. And this know-how was Telcordia qualified in the past, in the 2000s, something like that. And then we adapted it to go to space. So we have already some space-grade qualified components today. And as our colleagues, as you requested us to work on the quantum applications available, we created the micro-optic benches for quantum applications. So that was the idea of where we wanted to go.
Oh, okay, I see. And so now I'm trying to be in the shoes of the user. Say I want to integrate a specific optical function, such as frequency shifter or beam splitter. Can you do that?
As soon as the product, as soon as the component is available at your wavelengths, then we should be able to implement it inside the integrated micro-optical bench, okay? The tricky part is to collimate the beam. As we are experts in collimation and as we create our homemade collimators, we can easily do that. That's something that we can easily handle. As soon as the optical function is existing in the market today, we should be able to implement it, to fix it, to actively align it, and to create the perfect product for you. That's the idea.
Oh, I see. And at the end of the process, how do you ensure that you reach this level of stability and this level of robustness?
It's clearly linked to the capacity we have to be able to collimate beams with a high precision, okay? As soon as we can widen the beam, as soon as we can make it bigger, it's easier for us to focus it and to refocus it in the fiber, which means also that we will less depend on the variations such as vibrations, shock, and so on. So it's as we are able to perfectly work onto the collimation, it's the perfect way in order for us to achieve high power, to achieve stability, to be less dependent regarding all harsh environments. That's the idea, once again, of our know-how.
Oh, okay. So if I'm trying to summarize, your expertise is twofold. On one side, we have mastering materials, glues, specifications, and arrangement. And on the other side is mastering the assembly processes, the industrial processes linked to this small package, high robustness.
Exactly. That's clearly the idea.
Okay. And again, I'm still trying to be from the end user point of view. If I'm trying to, I have my lab experiment, I have my optical table, and I know I want to shrink the size of this particular part or make it more robust. How do I interact with you guys?
Typically, the customer's experience is as follows. We do have 3 steps. The first one would be your requirement, so your exact request. Usually, we ask you to draw us what you would like, what would be your perfect need, okay? Once we have your requirement, once we have your drawing, we can go to step 2, and then we will propose the exact optical layout that we could offer, and also the mechanical housing that we can think of, okay, depending on your constraints or your requirements, where you want to use it. If it's inside the lab, this is not the same request as in space, for example. And then the third step would be to go to the complete product, the real one, okay? And then the real product is, well, in this case, that was a product which was space qualified, which is actually in space, okay? And which has a particularity. This one is working onto the X and Y axis, as you can see the collimators on top right of the picture, but it also has a beam which is collimated onto the Z axis, for example. So this is the customer's experience that we can propose. This is from our feedback, this is clearly the easiest way to proceed in order for you to have the exact product for your requirement in the end.
Okay. And what are the typical tests that you carry prior to shipment?
Typically, we test the insertion loss, the PER, the power acceptance, depending if requested. We also make some tests in deep amp or in temperature tests. But then, once again, it will depend on your requirements, but that's the test that we typically offer.
Oh, okay. Okay, great. To move to a more precise example, because we understand that with these micro-optical benches approach, you can do whatever is available with free space optics. But there is also now some sort of catalog configurations that have been spotted and that are now available, I would say, on request, basically. And this is a nice example. I see a very clear drawing. What do you mean to show us here?
So this is the standard drawing of a 2x3 splitting combining proposal that we have. Okay, it's available on our datasheet on the website. You can see on the left the input fibers. Okay, then on the right the outputs, and you do have a functionality of a 2x3. You can notice here two photodetectors which allow you to monitor the power at each moment, okay, on the inputs, and then you go to your 3 outputs. The idea of this schematic is clearly to show you that it's easy for us to implement other functionalities on request, okay? For example, in this slide, you can see that we add one shutter on output 1 and another one on output 2, but we also add an acousto-optic modulator on output 3, which created for us the output 4, and which also acts as a frequency shifter, for example. But once again, we will be able to implement a shutter, for example, on output 4 or even on output 3. We can do whatever is requested for you, okay? That's the idea of our knowledge and of our customizing possibilities. Just a few words regarding the shutters. So you have to know that it can be used in both ways. The first one would be clearly to block the beam faster, okay, very fast, in order for you to have your quantum experiment really well made. And then the other one is also that it will avoid you to turn off your laser, which means that in the end, it will be a lot of time gained, because if you avoid to turn off your laser, then you also avoid the warm-up time of the laser, okay? So that's the idea, for example, of why integrating a shutter inside, or, well, and all this type of stuff. So that's the idea of the standard iMOBs.
I see, I see. And I see that this iMOB 780 series means that this particular works at 780 nanometers. Other wavelengths are available.
Yep.
But 780 is not a by chance choice, right?
No, it's not by chance a choice. It was dedicated at 780 because our colleagues from the quantum division had an interest. And maybe you can tell a few words about this interest.
Yes, indeed, because as announced at the beginning, we picked one application to help you understand why the iMOBs can be of added value, both in the lab and in the field. In the field of quantum technologies, several physical platforms can be used to perform quantum computing or quantum sensing. And one of them is cold atoms. So it's the ability to build up clouds of cold atoms with laser lights, and especially rubidium atoms with 780 laser light. And all at stake in this case is to have the necessity to bring light from different directions of space at a specific location in the vacuum system. This is very downstream. Upstream in the experiment, you usually have a few handful of laser systems that deliver the proper optical frequencies, especially two frequencies, cooling light and repumping light. And basically, you need some sort of photonic interface between the laser systems and the optical accesses of the vacuum system. And this is really what the means of the iMOB, and the iMOB 780 in this case. On the left, you have the picture of a typical intelligent laser system provided by iXblue for atom cooling and atom manipulation, with two fiber outputs. And this iMOB 780 here takes the two optical frequencies, it combines them, and then split the two frequencies among 6 outputs. And each of these fiber will reach the right precise location on your vacuum system so that you manipulate at will the atoms. And you mentioned that there is a whole of expertise about gluing the optical element to have something fixed and robust. Here, I want to make it clear that for this kind of application, there is the ability for the end user to still adjust the power ratio to make sure that the atoms will see exactly the power ratio that are needed science-wise. And once this setup is made, it remains super stable over time and over temperature. So, small footprint system, robust, that really makes the interface between the laser systems and the vacuum system. And this kind of iMOB can be integrated either very close to the laser system or very close to the vacuum system. And for us, this is easy. We just change the length of the fibers at the output or in the input. So one typical example, again, don't get us wrong, it is not only made for cold atom. We can use that for other parts of quantum technologies or for other applications in complex photonic setup. But the whole idea is to have something turnkey, integrated and robust with active components that get along with passive components in a very clever way.
Thanks a lot, Jean, for all this info. Yeah, thanks a lot to have emphasis that you're right onto some integrated micro-optical bench. It's also possible to have an adjustability regarding the power ratio for the combining splitting devices. So you can fix it to the right value requested for your magneto-optical trap. But it's always nice here to see how the iMOB is creating the link from the emitter, from your own laser source to the magneto-optical trap you are using. In here, you do have the picture of the internal of an iMOB, okay? And you can see, for example, the acousto-optic modulators, the mirrors, the polarization beam splitters, plus the variable half-wave plates, quarter-wave plates that we are using in order for you to be able, for example, to adjust these ratios. Just to finish this presentation, I'm going to the slide of conclusion, some take-home messages that I would like you to keep in mind. I would say that the first one would be the possibility to integrate everything. So once the power ratio is adjusted by you, there is no need anymore to optimize the alignment nor than to clean the optics. Clearly, once again, we are emphasizing the time which is gained for you. Then the second one would be the robustness. Our technology is Telcordia qualified, and for some of it, space grade qualified, and we can work on it depending on your request. We can go up to your requirements if needed. The third one would be regarding the polarization quality. We know that it's tricky for you to handle the PER, to handle polarization. Our iMOBs are made with a typical PER around 30 dBs, okay? And this is done because we know that for your quantum experimentations, it's a key point to have the highest PER available. And the last one would be, once again, the small footprint. iMOBs modules are developed to be compact and small. They can be equipped with input and output fiber lengths of several meters, okay, as Jean said a few minutes ago. Clearly, this is because we want you to be able to place it wherever you want, even if you want to integrate it inside an instrument, or if you want to integrate it inside your lab with 10 meters fiber length, for example. That's all about we want you to remember from this presentation.
Thank you, Etienne. It was a pleasure to have you. It's really exciting to have this iMOB technology now available. Both aspects, fully customized on demand, but also some catalog products. You will find all the information on our website, and feel free again to shoot us email for deeper technical inquiries. Now we are able to welcome questions. So should you have some, really feel free to write in the chat box and we'll try to answer as best as we can. First question from Ellen. Is there current limits to the compactness of your series of products?
Yeah. Well, of course, there will be a limit to the compactness because it will depend on the functionalities required, okay? Let's say that if I want to integrate an acousto-optic modulator into an iMOB, well, I need the iMOB to be bigger than the acousto-optic modulator. So in a way, there will be a limit to the compactness. But on the other way, I would also like to say that we are trying all the time, when we are proceeding to the optical layout, we are always trying to compassify everything. Our idea, for example, is, if available, to use just one mirror with several spots onto the mirror. For example, to use it with several beams at the same time, instead of using 5 mirrors for 5 beams, okay? So that's the idea of how we can compassify everything. So then it depends a lot on your request, but yeah, there is a limit of the compactness, even if we will always try to make it smaller if possible.
And for iMOBs, I mean, if I remember what you explained us, typical size is 8 by 15 centimeter by 2 centimeters. So that's the
roughly
typical.
That's it, yeah. Roughly. Any other question?
Yes, Julien. What is the price scaling for micro-optics on 1 unit, 10 units, 100 units?
The price would depend, once again, on the functionalities you would require. The price range for the integrated micro-optical bench is going from 10 to 20,000 euros for standard versions, I would say. Then for several units, clearly we would need your drawing first. We would need to work on it. We need to know what is the challenge you are facing, and then once we have all this information, we will be able to make a more precise quote, I would say.
And in the end, it's also that, as you explained us in the description of the customer experience, the team is really a technical focus and a commercial focus. So we will be able to go hand by hand with you to reach first the best design, the most cost-effective design, and also to work out on a good commercial proposal to really meet your need and the volumes and the lead time. These are the typical aspects that we will handle.
So new questions from Shiji Chai. So all the optical components are glued to the base. Yes, not exactly to the base. We will use a substrate from the base of the mechanical housing and the optical elements. So it's not exactly glued to the base. There will be a substrate within, but yes. Yes. Any other question?
Another question regarding temperature. What is the typical temperature range that we check to accept the manufacturing? The top of my head, this is 10 degrees C to 55 degrees C.
Yeah, I had in mind something from 10 to 40, but then I would say that it will depend on the optical elements that we will place inside. So we can make with development, we could make something which is completely hermetic, for example. So maybe we could achieve a wider specification, but it will depend in a way also on the photonic element that we will place inside. So it's quite a tricky question. Without the complete requirement, it's really complicated for me to answer that. But yeah, typically from 10 to 50, 10 to 40 is no problem for us.
And it means that for most of the use on ground, the iMOBs are fully qualified and there's no question. Being in the lab or outside of the lab, this is
exactly
usually all good. A new question. Can you integrate other more alignment precise devices, such as a quadrant photodiode, in your system?
I wouldn't see why we couldn't. So this should be perfectly feasible. We would need the specs of the QPD, the quadrant photodiode, but I think it's something that we should be able to achieve. Once again, if it was possible for you to send us the drawing, you will have just let me skip to, okay, you have here my email address. So it's etienne.decerle@iXblue.com. If you can send me all the info, then we will be able to to take a look at it and to check that it's perfectly feasible. But from top of my mind, I wouldn't know why we couldn't. So
I see. So new question, for how long do you guarantee the stability of the system?
Well, I think some tests have been done over, if I'm not wrong, years.
Yes.
Because one of the, well, some of the iMOBs were integrated inside the laser that we showed at the beginning of the presentation, which was on the top of Mount Etna for more than a year. And the stability was still the same at the end. So, yeah. Well, I wouldn't say that we tested it over a year, but the results over a year were good.
Yeah,
let's say so.
So it's hard to guarantee, to really commit contract-wise for, let's say, 5 years of duration. But experience shows that for our quantum gravimeters, but also for other products that have been deployed and sent into space, that year-long stability is now routine, and you can really count on that. What is the estimated lead time for such system?
Typically, the lead time is from 12 to 16 weeks. Actually, we do have a lot of work, so I would say that we are closer to 16 weeks than to 12 weeks. But then, once again, it will depend on the functionalities requested inside. Okay, we have some requests, for example, at the moment to implement some SHGs functions, so second harmonic generators functionalities inside the iMOBs, which is perfectly feasible. But as soon as we are speaking about that, we also depend on the lead time for the SHG crystal, and the lead times for SHG crystals are, for the moment, very long. We are close to a year, I think. So, depending on your specification, depending on your request, it might be long, but well, it depends really on the specification of the functionalities you require inside.
But you would say that I would say under normal circumstances, typical lead time is 12 to 16 weeks.
16 weeks, yeah, something like that. For the standard versions available on the datasheet, 12 to 16 weeks, maybe 18 weeks, but this is the range we are speaking about, yeah.
Okay. A question from Julien, what is the maximum optical power rating?
What is the maximum optical power? Max optical power would be around 1 watt, 2 watts, a few watts, okay? Inside the product, we are not limited by the optical power, okay? Because we widen or we broaden the beam. So as the beam is bigger, we do have a lower density for the optical power, so it's no problem inside. The critical problem or the critical side is regarding the connectors, okay? You do have to clean them before the first connection, and these are the critical part regarding the optical power. So if you require for high power, we would need then to work with you regarding the definition of the connector you plan to use.
Okay.
So that's the idea.
Okay. You're welcome. If there's no question, thank you very much, everyone. Thank you, Etienne, for such a level of detailed information. We remember that you're available for more technical and precise inquiry. I recap that we have also some data sheets available on the website, and that this webinar will be available in replay, in live later on after a good night's of sleep. Thank you for being with us.
Thanks a lot, Jean. Thanks to all the audience. Thanks a lot, Fritz. Thanks a lot to all of you guys, and thanks a lot to all the support team, which you can see on the video. But thanks a lot to everyone, and have a nice day.
Thank you. Bye-bye.